Welcome to This Explainer. Today, we're diving straight into the invisible but absolutely massive industrial processes that scale chemical reactions up to create our modern world. Everything around us, from the plastics in your laptop to the fuel in your car to the active ingredients in your medication, relies on chemical engineering. But here's the thing. Taking a chemical reaction that works perfectly in a tiny, highly controlled laboratory setting and making it work on an industrial scale, well, it's honestly one of the most complex engineering challenges on Earth.
Now, what's genuinely fascinating is the monumental jump in scale from a single laboratory test tube to a sprawling industrial chemical plant. You can't simply take a beaker, make it 10,000 times larger, and expect the same results. It's kind of like trying to bake a cake that's 10,000 times larger than normal. You can't just throw it in a massive oven and expect it not to burn to a crisp on the outside while staying completely raw in the middle. When you increase the volume of a reactor, the physical dynamics of heat and mass transfer change dramatically.
And that brings us to the core question of our explainer. How do engineers bridge that terrifying gap without blowing everything up? Because, let's be real, if a reaction gets too hot in a test tube, it might just bubble over. But if it gets too hot in a 10,000-liter industrial tank, it can cause a catastrophic explosion. So today, we're going to explore exactly how scientists conquer the extreme physical challenges of taking a microscopic reaction and scaling it all the way up to profitable, steady-state production. Let's get into it. Part 1, the heart of the plant.
This right here is the ultimate destination for any commercial process. It's literally the heart of the plant. The reactor continuously converts raw materials into products before sending them through downstream separation units like a distillation column. In these massive facilities, the primary goal is no longer just scientific discovery, right? It's about maintaining steady-state, profitable production, all while ensuring flawless product quality and absolute safety. While operating data at this level provides the closest approximation to actual industrial conditions, we run into a major roadblock. As the saying goes, physical limitations can disguise the true kinetics to a significant degree. What does that actually mean for us? It means things like the time it takes for heat to dissipate or fluids to mix become the limiting factors. They basically hide the actual speed of the pure chemical reaction itself. And to make matters worse, you can't just run wild experiments at this massive scale to figure out what's going wrong. It's strictly forbidden due to safety hazards, immense costs, and the simple need to keep production running. Section 2. Bridging the scale-up gap. So if we can't safely test our theories in a massive factory reactor, what do? Well, we use a half-large-scale bridge known as the pilot plant. Pilot plants exist purely for information gathering and verifying mathematical models, which is a stark contrast to factory-scale reactors that have to maintain profitable production. A pilot plant might consist of just one or two full-size tubes of a reactor, rather than the thousands you'd find in the final factory. It's that absolutely critical intermediate step where laboratory-derived kinetics finally meet conditions that resemble industrial reality. What's really wild here is the way engineers use these pilot plants. Instead of using a mathematical model to dictate how big the reactor should be, which, is the standard design approach, engineers actually use a reverse design procedure during these dress rehearsals. They run the pilot plant, measure the output data like outlet concentrations and temperatures, and then use that data to calculate the effective reaction rate. From there, they compare that real-world rate to their laboratory mathematical models and tweak the parameters until they get the absolute best possible fit. So this pilot data helps analysts rigorously tease apart the intrinsic chemical kinetics, the pure chemistry, from physical limitations like heat and mass transfer. Pilot plants allow engineers to find dangerous temperature hotspots way before they're built into a final factory. They also use really rigorous experimental testing like residence time distribution, or RTD for short. This involves injecting tracer substances to track exactly how long fluids stay inside the reactor. It's a brilliant technique, but it simply isn't allowed in the final factory because obviously you can't risk contaminating the commercial product. Part 3. The Catalyst Separation Challenge. Let's zoom in on a very specific, microscopic operational headache. Think about a traditional slurry reactor. To speed up chemical reactions, engineers use catalysts, right? Well, in slurry reactors, tiny, highly active catalyst particles are mixed directly into the liquid reactants. Because they're so insanely small, they provide a massive surface area for the reaction to take place, which is fantastic for efficiency. But they create a massive problem at the end of the process. It's kind of like trying to get fine sand out of a swimsuit, but scaled up to a multi-million-dollar industrial facility. Which leads to a huge problem.
How on earth do you catch a microscopic catalyst once the reaction is done? Just imagine the absolute nightmare of trying to separate microscopic, powdery dust from your final liquid product on an industrial scale, thousands and thousands of liters at a time. Traditional separation methods like filtration or decanting, which is basically just letting the dust settle to the bottom, are incredibly difficult and inefficient with these fine particles. And here is exactly why this matters. If you fail to remove all that microscopic dust, escaping catalyst fines will cause catastrophic deposits. They will literally erode your downstream equipment, tearing up super expensive pumps and heat exchangers. It's an engineering nightmare for sure.
Part 4. Monoliths and Taylor flow. To eliminate this separation disaster, engineers came up with some totally ingenious microstructural solutions. The first is the monolith reactor, which is brilliantly described as a frozen slurry reactor. Instead of a giant tank full of floating dust, a monolith is a single solid block, usually ceramic or metallic, that features a multitude of vertical, parallel channels. The active catalyst material is fixed directly onto the walls of these straight channels as a thin layer called a washcoat. So you get the incredible surface area of the microscopic catalyst, but it's frozen in place. Nothing escapes. Zero downstream erosion.
But wait, how do you get the liquid and gas to mix perfectly if the catalyst is literally glued to the walls? The secret to their efficiency is a mesmerizing fluid dynamic phenomenon known as Taylor flow, or slug flow. When you force gas and liquid through these incredibly narrow channels, they organize themselves into an alternating pattern of gas bubbles and liquid slugs. It's really something to see.
Notice exactly how this builds efficiency. By restricting the channel diameter, engineers physically force the gas bubbles to expand until they fill the entire cross-section of the channel. As that gas bubble pushes through, it creates micrometer-thin liquid films against the catalyst-coated walls. And as the alternating slugs of liquid follow the gas, the tight confinement induces powerful internal recirculation, basically local turbulence within the liquid itself. This mechanical mixing rapidly transports the reactants straight from the center of the channel directly to the active catalyst on the wall. It's highly controlled, incredibly efficient mass transfer without any floating particles to worry about later.
Section 5. Catalytic packing elements. While monoliths are absolutely perfect for certain reactions, our second architectural solution takes a totally different yet equally fascinating approach. Where monoliths use straight channels, catalytic packing elements like catapack modules abandon straight lines entirely. Instead, they use a complex, intertwined network or mesh. The catalyst particles are trapped within this physical structure. As the fluid is pumped through, the intricate construction forces the fluid to constantly redirect and twist. This creates intense static mixing and local turbulence, enhancing the mass transfer by physically forcing the molecules to crash right into the catalyst. Comparing these two side by side really highlights the genius at play here. Monolith reactors use continuous parallel channels and rely on that alternating Taylor flow, while catalytic packing elements rely on complex meshes and static mixing. But the absolutely crucial point is how they handle the gas phase. In a monolith, gas and liquid flow together, right through the exact same channels. But in catalytic packing elements, the structure actually segments the phases. Because the mesh enclosing the catalyst is so small, sometimes just half a millimeter, gas bubbles are physically restricted. They remain exclusively outside the catalyst network, while only the liquid penetrates it. Because of this unique, segmented phase distribution, packing elements are the absolute ultimate choice for a process called reactive distillation. Remember that distillation column we discussed earlier? Well, reactive distillation allows the chemical reaction and the separation of the products to happen simultaneously, right there in the exact same column. It's a total marvel of process intensification, saving massive amounts of space, energy, and money in the chemical plant. So from the massive, sprawling factory floors down to the micrometer-thin fluid films inside a single ceramic channel, the sheer ingenuity of scaling up chemical reactions is honestly breathtaking. Engineers have learned to manipulate physics, fluid dynamics, and microscopic architectures to safely deliver the materials our modern society completely relies on. And it leaves us with a pretty fascinating thought. As we continue to push for greener, more efficient processes, what new invisible architectures will engineers design next to power the next industrial revolution? Thanks for joining me on this explainer. Keep wondering, keep learning, and I'll catch you next time.